So today's video is on nucleophilic substitution. So first we're going to have a look at a few key definitions. So first is a nucleophile, and a nucleophile is a electron pair donor. So this is a molecule with a partial negative or full negative charge that donates electron pairs. And then we have a substitution reaction. So this is a reaction where one group in a molecule is replaced by another. And then we have steric hindrance, and this is when molecules are in the way. So when a molecule is in the way of another, and this is stopping a chemical reaction from happening, and we'll look into this later. Then there is dissociation, and this is the splitting of a molecule. So this is breaking bonds to split the molecule. So SN1 and SN2. SN1 is unimolecular. So this is a type of nucleophilic substitution when the reaction occurs depending on one molecule. So when the reaction occurs depends on one molecule only, and SN2, bimolecular, is when the reaction occurs depending on two molecules. So when this reaction happens, depends on two molecules instead of one. So first we're going to look at an SN1 reaction. So this is unimolecular. So we start with a tertiary haloalkane. So this is our central carbon is bonded to three other carbons. And the bromine is more electronegative than our carbon. So we can see our central carbon here is attached to a bromine. So this is what makes our haloalkane. So our bromine is more electronegative. So it attracts these bonding electrons more. So it pulls these electrons closer to the bromine, inducing the bromine's partial negative charge and inducing a partial positive charge on the carbon because the electrons are closer to the bromine. And if you notice, the methyl groups attached to this carbon, so here, here, and here, these all also have a tetrahedral shape. So we can see that this overall molecule is tetrahedral, but these bonded groups to our central carbon are also tetrahedral, and this is important. So now a negative hydroxyl comes along, and this is a nucleophile. So as we said before, this has a negative charge, so it's going to be an electron pair donor, making it a nucleophile. And so this wants to attack our positive carbon. And remember, our carbon has a partial positive charge because bromine is more electronegative. And our negative charge on the bromine repels this hydroxyl, this nucleophile. So this bromine repels the like negative charge. So our hydroxyl, even though it wants to attack this positive carbon, cannot attack the carbon from the top because of this bromine's negative charge repelling it. But also, because of our tetrahedral methyl groups, these cause steric hindrance. So if our hydroxyl tries to attack from below, these molecules are in the way because they're large tetrahedral molecules in themselves. So this causes steric hindrance. This hydroxyl cannot get to the carbon. So this means that the hydroxyl cannot do anything. So it cannot react with this positive carbon like it wants to because it cannot get to the carbon through the negative charge of the bromine or through the steric hindrance of the methyl groups. So the hydroxyl has to wait for the bromine to spontaneously dissociate. So this dissociate is breaking the bond. And so this is why it's unimolecular. This is why it's SN1, because the hydroxyl does not dictate when the reaction happens. It's only this bromine. The molecule has to dissociate before anything can happen. It's only this molecule, this bromine atom, that determines when this reaction happens. So after the bromine has spontaneously dissociated, there's no now negative bromine to repel the hydroxyl group. So the hydroxyl can now attack this new carbocation. So you can see here that our bromine has spontaneously dissociated, and so there is now no negative charge repelling this hydroxyl, allowing it to now attack the positive carbon. So now after our hydroxyl attacks this positive carbon, donating an electron pair, it forms a single covalent bond. So this hydroxyl and carbon now form a single covalent bond, as you can see here. So this forms the product, and it's a simple substitution of the bromine. So this means, as you can see here, our original, and so you can see that there is a bromine here, and now on our new product, you see we have a hydroxyl here. So we've just replaced the bromine with this hydroxyl. There's no other change to the molecule. So these 3 methyls are still in the same position as before. So we've just simply replaced this atom with this group. And you also need to notice that the carbon-oxygen bond in our product has a higher bond enthalpy than our carbon-bromine bond in our original molecule. And this is because bromine is a larger atom, it has a lower charge density, it has more electron shielding. So this means that the carbon-oxygen bond has a higher bond enthalpy. So it's unlikely that this reaction will reverse. So it's unlikely that this bond will spontaneously dissociate to allow the bromine to reattach. It's more likely that the bromine will dissociate and allow the hydroxyl to attach to the carbon than the other way round. Next, we're moving on to SN2 reactions. So this is bimolecular. And we can see that we have a secondary haloalkane. So our central carbon is bonded to 2 other carbons in our methyl and our ethyl group. And you can see that it's also bonded to a bromine, which makes it a haloalkane, and it's bonded to another hydrogen. So our bromine again is more electronegative than our carbon. So it induces a positive charge on our carbon, and this is because our electrons are being more attracted to this bromine. So the electrons get further away from the carbon, inducing this positive charge. And our hydrogen is very small. So it's much smaller than our methyl group that we had last time. And so it's a reduced steric hindrance. So this hydrogen by itself is not a tetrahedral like our methyl in our SN1. So it has limited steric hindrance. It limits the amount of blockage to the carbon. And this is a tetrahedral molecule. So the bond angles are 109.5. So our hydroxyl comes again. And our hydroxyl has a negative charge, so it acts as a nucleophile, and it wants to attack the positive carbon like before. So our hydroxyl is on the opposite side. So our hydroxyl before was attacking from over here, and this means that it is not repelled by the negative bromine. Because it's on the opposite side of the molecule, this negative charge on the bromine cannot repel this negative charge on the hydroxyl. And our hydrogen, as we said, has reduced steric hindrance, so it does not block the hydroxyl from attacking the carbon. And so this means that the hydroxyl can attack the positive carbon without any spontaneous dissociation needing to happen. So this is why SN2 is bimolecular. The hydroxyl now dictates when the reaction starts. So when the reaction starts depends on 2 molecules. It depends on the molecule reacting, and it depends on the hydroxyl. Because the bromine doesn't need to spontaneously dissociate, the hydroxyl can attack on its own accord. And then after the hydroxyl attacks the positive carbon, it goes into a transition state. So our hydroxyl and bromine now have partial bonds with the carbon. So you can see here that our hydroxyl has attacked this positive carbon, forming the partial bonds. So the dotted lines represent the partial bonds of bromine and carbon and our hydroxyl. But because these bonds are only partial, the transition state is actually in trigonal planar. So you can see here, this is what our molecule looks like without the partial bonds. So it has a 120-degree bond angle because it's a trigonal planar, because these partial bonds don't contribute to the overall shape of our molecule. And so the central carbon now has a high electron density, and this is because it has a partial bond with bromine and our hydroxyl, and it has full bonds with 3 other atoms. So this means that our carbon is now unstable because it has more bonds, more electrons than it vouched for in the beginning. So our carbon needs to remove one of the partial bonds to remain stable. So the hydroxyl is a much smaller molecule. Our oxygen is a much smaller atom. So this means that our oxygen has less electron shielding than our bromine. It has a higher charge density than our bromine, and it's more electronegative than our bromine. So this means that our oxygen and our carbon have a higher bond enthalpy than our carbon and bromine. So this carbon-bromine bond has a lower bond enthalpy than our carbon-oxygen bond, and this is because our oxygen is smaller, it has less electron shielding, a higher charge density, and is more electronegative. So this bond length is shorter, it needs more energy to overcome. So this means that our carbon breaks the bond with the bromine because it requires less energy to break this bond. So the bonding electrons in this partial bond with our carbon and bromine attack the bromine atom to break this carbon-bromine bond. So this now means that our hydroxyl can form a proper bond with our carbon. So it's no longer a partial bond, it's no longer a dotted line, it's formed a full single covalent sigma bond. And now this hydroxyl bond has formulated, it now repels the others. So it repels the hydrogen, the methyl, and the ethyl. So now our molecule wants to go back to its tetrahedral shape. So it wants to get back this 109.5 bond angle. So in our transition state, it was a trigonal planar because it had 2 partial bonds, but now it's formed a proper bond. It wants to go back to this tetrahedral shape. So the easiest way for our molecule to now revert back to the tetrahedral, our 109.5 degree angle. The easiest way to do this is to flip or inverse our ethyl group. So this is the group that goes into the page, so it's the dashed lines. So by inverting this to the other side, it gets back its tetrahedral shape easier. So this is an optical inversion. So you can see here that our original molecule has our methyl in the middle, and it has our ethyl to the left. And in our new product, the ethyl is now to the right. So it's flipped. It's been inverted. It's an optical inversion.